sort of do controls. So closed chain modeling. So it's going to be slight repetition, but it's slightly different from what I did earlier. Then dynamics, simulation, and then finally end up with control partitioning. Okay, and so the general of I'll talk about in this case a 4-link chain, not a 5-link chain. So a 4-link chain could be like this: 1, 2, 3, and 4. Okay, and so there's no reason why this point and that point should be the same. But in this case, we'll look at two specific leg geometries which have been used to create legged robots. Leg geometries. Okay, and the motivation will be to take those geometries and model and control them. Okay, so one is this geometry. It's a different color. So okay, so that's one. The second one is this one. The third one is actually a repeat of this one. It's different in some way. I'll tell you in a bit. Okay, so these are the 3 geometries. Now, two of them look same, but they're different in some way. I'll show you in what way they're different. So this geometry has the red links are basically the links of the same size, and the blue links are the links of the same size. Now, this one, the first one, so let's let me call this link the angle made by the red link with the horizontal, the left link, red link with the horizontal be Q1, and let's call this as Q3. Okay, I wrote Q1 and Q3 because there is a motor at Q1 and Q3. So this motor basically enables you to move the red links with respect to the horizontal. And the other links do not have a motor, because in this case, if it's a 4-link manipulator with a closed chain, then it only has 2 degrees of freedom, which are free, and the rest 2 are functions of the other 2 ones. So that's basically something which I will show you a little bit later on. But for now, just believe me. This is a leg design which can be seen in the robot monitor. Okay, and this is the one which Jeremy is using. Okay, this one has motors at similar places. So Q1 and Q3. So again, motors at Q1 and Q3, and this is used by a robot called Atreus. If you search for it, you'll see the robot. It's so this is the Q1 and Q3 are the same angles controlled for both these leg geometries, but they have different link lengths. That's all the difference. And here, what we're going to do is, this is Q1, and let's call this Q4. And so here there are motors at Q1 and Q4. Okay, and this is the leg on digit. Is that right, Ernesto?
Let's see, Q1. Mm, no, it's actually so look, Q1 is fine, but then there's another one on Q one, two, what would it be?
You
So I
mean
think
here? No, I don't think so. I think it's on this joint, right?
yeah, but the link lengths are incorrect. The long links should be the short links.
Oh, don't worry about the links. I can change the links anytime.
Yeah.
I can change the
Um,
reds to be longer than the blues. I'm just wondering if this is how the motors are. This is, I thought, was a hip joint at Q1, and then Q4
mhm.
was the knee joint. Okay, anyway, we can change it later on. I'm just want to, uh, okay, since this is question, we have to check this, but it really doesn't matter. What I'm going to show you is very generic. It can be used. You
I
can,
think
yeah.
I think in that case it would be Q3 and Q4.
Q3 and Q4. Okay, not a
Yeah.
big difference. Okay, but
Yeah.
okay, so my notes are for Q1 and Q4, but changing it to Q3 and Q4 is very trivial, as I will show you. Okay, so I'm going to do this with these just geometry just because it corresponds to my MATLAB code, but changing to Q3 is easy. Okay, so there are this different geometries and different lengths and different angles which are actuated, and I will show you how to uh, model this first and then control it, and then the control will actually rely on the fact that these motors are at different places. So the first thing is, let's talk a little bit about modeling, and then once you have that, control is will follow. Okay, so modeling. Okay. Now what I'm going to do is I'm going to make a very generic model, even though it's a chain like this or like this. I'm just going to what I'm going to do is I'm just going to assume that the lengths are totally different. So L1, L2, L3, L4. And the other thing, important thing is I'm actually going to cut it at a different place or separate the links at this place. I'm going to separate them here. So in the last time I talked about closed chains, I actually cut this link. And so it was it was basically this. It was a 4-link pendulum like this. And then I joined this to this point using a closed loop constraint. In this case, I'm going to do it differently. So I'm going to cut it right in the middle. And so in that case, I will have two pendulums. Okay, that's pendulum one. And the other pendulum, I'm just going to assume it's at some different place. Okay, of course, I can make these lengths go to 0, and I'll recover my um, position for or the angles for the closed loop geometry that I just talked about. So this is Q1, this is Q2, this is Q3, and this is Q4. And then L1, L2, L3, L4. Okay. The first step, let me just call this 0. Let's call this P1, P2, P3, P4, and let's call this O prime. Okay. Okay, so the modeling is essentially you model the double pendulum on the left, you model the double pendulum on the right. And so when you do that, you basically write the Lagrangian of uh, pendulum one. Okay, you can write that down, that's not hard. And you write a Lagrangian of pendulum two. So this is 1 and this is 2. And that is going to be some function of Q1 and Q2, right? And a Q1 dot and Q2 dot. And this is going to be some function of Q3, Q4, Q3 dot, Q4 dot. Okay, so once you do this, the key step here is when you take these, so then when you take these equations, so dli dq dot minus, So d dt of this, and then dli dq equals q j. Okay, so when you take these equations, the key thing to do here is instead of having q j as just q1 and q2, you just do it everything q3 q4. So what will happen is you will get this big matrix with lots of zeros, because for the first equation you only have q1 and q2 is, so L1 is a function of Q1 and Q2. So anything with Q3 and Q4 will be 0, and anything with L2 involving Q1 and Q2 is going to be 0, because there's only Q3 and Q4. So you need to run this for four variables: Q1, Q2, Q3, and Q4. And what that does is it basically gives you an equation which looks of this form. See, just write on the new page. M Q double dot plus N equals 0, because the external torque, let's assume that the external torques are 0. Okay, and then Q is Q1, Q2, Q3, Q4. Now, these are 4 equations. So 4, 1, 4, 1, 4, 4. Now, what we need to do here is we need to connect this point with this point. So what I need to do is find the coordinates of P2, which you can see here is something like L1 sine of Q1 plus L2 sine of Q1 plus Q2. So you can write the coordinates of X P4, which again comes there, L3 sine Q3 plus L4 sine Q3 plus Q4. Okay. Similarly, you can write the Y coordinate P2 Y P4. Okay, so once you do that, then you can write X, let's call that XP2 as, and this is capital X, is XP2 YP2. And capital X P4 is small x P4, small y P4. So you've got this. Now, what you need to do is, we can see that for this system to be a closed chain, the coordinates of X P2 should be equal to X P4 and Y P2 should be equal to Y P4. Or in other words, capital X P2 for chain, we can say that X P2 should be X P4, right? Where X is the capital X, and that encompasses, this might be easier. P2 should be equal to X P4, and then X has the small x and y, small y, which corresponds to the X and Y coordinates of the end of each two-link pendulum. Okay, so this should be true. So now what we can do is, we can now take the Jacobian of this. Okay, JP2 Q dot equals JP4 Q dot, where Q is the same as this. So you need to take the Jacobians against all 4 variables. Okay. Okay, so that's true. And since we got it, we need to get it at the acceleration level. So this is our formula. Let me just write. This is 1. Since I need to get it at acceleration level, I need to differentiate this expression again. So I'm going to differentiate again. So J P2 Q dot plus J dot P2 Q, so second derivative, sorry. So that should be double dot, and then this should be dot for J dot equals J P4 Q double dot plus J P4 Q dot. It looks good. Yeah, it looks good. And so what I can do now is, I'm going to pull all the Q double dots together. So I have JP2 minus JP4 Q double dot equals minus JP2 dot Q dot plus J dot P4 Q dot. Okay, so what remains to be done now is to put all these equations together. So this is 2. And then 1 was here. It was simply mq double dot plus n. So I'm just going to write that down as an easy reference. So I earlier got mq double dot plus 0. By the way, n is, if you know, it's the Coriolis force. So it's c q dot, and then there was a gravity term. But that's all clubbed together. So now let's take equation 1 and equation 2 and put that together. So we have m. Oh, my bad. I'm forgetting something. Right. So this equation, by the way, is the equation of the two pendulums when they are not interacting with each other, which means that they're not connected at P2 and P4. If they are connected at P2 and P4, there will be a force at P2 and P4 which will keep them together. So that force is a part of Qj. So I need to modify equation 1. So let's do that first. So we need to, this is unconstrained. So I need to constrain it. So the way I constrain it is, if I have a pendulum like this and another pendulum, I'm going to put it like this. So they are joined. That's going to be a force P, which will keep them holding together. Let me call that F here, just not confuse it with P2 and P4. So this is P, P1, P2, P3, P4. Okay, so I need to change this. So I need to add a Q. So in this case, what I do is mq double dot plus n equals the constraint force. So if this force F acts at P2, then the same force will act in the opposite direction at P4. Okay, and so the way we constrain this is we take the Jacobian of P2 and take the transpose and multiply with F. And that's how you get the effect of the constraint force on the system dynamics. Since this F is opposite direction, I need to put a minus. So, or I can put JP4 transpose times minus F, just because that force is in the negative direction. So now I can write this as MQ double dot plus N equals JP2 transpose minus JP4 transpose times F. So this is the equation for the constrained system. Okay, so this equation is, say, 3. And now my goal is to take the constrained equation, the equation number 3, and take equation 2, which is basically tells me something about the constraint, and put it all together. So from 2 and 3. So I can write this as M. I would need to move this to the other side of the equation. So this becomes minus JP2 transpose minus JP4 transpose. And then this part is written down here, which is the other equation. And then this is 0 because there are nothing related to P there. So there'll be Q double dot, and there'll be F equals minus N, because this N has gone the other side, and then corresponding to this, I'll have to put this there. So minus JP2 plus J dot P2 plus J dot P4 times Q dot. Okay, so this is my grand final equation. Okay, and that's when the torques at the joints are all 0. Okay, there are no torques appearing here. So this is the unconstrained system. So first, let me show you a simulation of how the system looks like. Okay, and then we can proceed with other things. Okay, so first I'll show you this is a standard derivation of two double pendulums. Okay, so if you it basically took two pendulums, I wrote the equations and I simulated them. Just let me stop this. Okay, let me first show you that they do the same thing. So this is basically the initial conditions. So the first pendulum has four initial conditions. I set it the Q1 to be pi by 2, velocity to be 0, and then for the other one 0, 0. For the other one pi by 2, 0, 0. So now if you run this, you'll see the same behavior. That is, they very much do the same thing. Okay, now let me change the initial condition, one of them. Okay, and not by a lot, but just a teensy bit. I'm just going to change one of them from being pi by 2. I'm going to add 0.01 radian to one of them, and now run it. So it looks similar, but then you can see that now they're diverging. Okay, so this phenomenon, which is basically a sensitive dependence on initial condition, is called chaos. So if you start to a pendulum with slightly different initial condition, then the behaviors are going to be very different from what it was without that perturbation. And so many systems like weather prediction are actually chaotic. So the more good guess you have on the initial conditions, the higher is your probability of predicting that it's going to whatever, it's going to rain or it's not going to rain. But so that's why when you see the weather prediction, they'll be like 10%. They predict 90% chance of it raining, and then when you come closer and closer, you see that the chances go down to 0% sometimes. That's because they cannot predict what will happen based on their weather models. So it has very high dependence on initial conditions. Okay, that was an aside. Now, so next, let me show you dynamics of a four-link chain. So now what I'm doing is, this is just an extension of the five-link simulation I did some time back. So I derived the four-link chain. Okay, essentially this goes through the whole process. Essentially copy-pasted the code from double pendulum. The only difference being that I now compute the Jacobian. I should have done, yeah. So I compute the Jacobian and J dot to get those equations. So once I have those equations, then I can simulate this. Now, when you're simulating, again, you need to remember one thing, that you need to start this model such that it's the chain is closed. Okay, so that the P2 is equal to P4, the x position, y position of P2 equal P4. So I need to solve this, use fsolve to solve for that conditions, for the angles so that that condition is met. So I use fsolve here to ensure that the chain is closed. I also need to ensure that the velocities are consistent, right? You cannot have P2 velocity of P2 to be different from velocity of P4 when it starts. And if you do that, then it will behave in a very strange manner. So I do that, and then it's regular ODE 4.5. I'm going to run this, and I'm going to specifically do it for these models. So Minotaur leg, which is the leg with two links. Yeah, so this is the model with the first top two links of the same length as each other, and the bottom two links of the same length. And then I can do it for the digit leg or Atreus leg. Now it's a parallelogram. Okay, so that was how it is. So now, next part, I'm going to show you how do you control this leg so that it swings from one position to another position. And remember, we're controlling two joints simultaneously. And like the simple prismatic leg and prismatic leg revolute joint hip leg design I showed you in one of the Coppelia sim class, that was really independently, you could control both those degrees of freedom and you could get to wherever you want. But here it's coupled, and that coupling is what makes it challenging to control. And I'm going to show that to you, but let's take a 5-minute break. To controlling a closed loop chain. Okay, so before that, I want you to remember this equation. So let me just take this equation. I'll write this slightly differently. Let's take this. Copy. So for all practical purposes, we can rewrite this as M minus J transpose J0 Q double dot F equals minus N minus J dot Q dot, right? Where in this case for 4-link chain, we have Q equals Q1, Q2, Q3, Q4, and F equals the force in the X direction, force in the Y direction. Okay, so something I should have mentioned this, I didn't quite do it, which is when you have a system like this and like that, so two pendulums with Q1 and Q2, Q3 and Q4. So there are 4 DOFs, right? So 4 DOFs are here. And now if you want to make that into a closed chain, then you want this joint P2 to be the same as location as P4, right? So when you take P2 and connect it to P4, you have 2 constraints. Okay, so or in here, there are 2 forces, Fx, Fy, which help you to keep P2 connected to P4. So the net DOF is 4 minus 2, which is 2, which means that the system has only 2 degrees of freedom. That means you can only apply 2 torques to the system. The remaining 2 joints are going to be moving as a result of being a part of this closed chain. So there will be 2 torques that can be applied. Now you could have more torques, which is called over-actuated system, but it'll cause all sorts of headaches. I would just avoid that for now. We just assume that there are 2 torques here, which can be applied at the 2 joints, and you can choose which 2 joints. In this case, the 2 joints are going to be the places where you're going to put the motors. So I showed you that for the Atrius leg, there are different places compared to the digit leg. And Minotaur basically has the same places where the Atrius leg has the motors. So you can choose which cues you're going to apply the motor torque. So I'm going to try to keep this so that you can do it for any system. You can choose wherever you want to put the torques, and this what I'm going to show you will hold. Let's talk. Let's recollect what we did for the control partitioning or feedback linearization. Feedback linearization. And we'll do this for the simplest thing, which is the of 2-link chain or a double pendulum. So Q1, Q2. So the equations for that was MQ double dot plus N equals the torque. In this case, the torque, or let's call that U. The U are the torques at T1 and T2. So U is T1, T2. And then Q is Q1, Q2. Okay. And so when we wrote down U as Q double dot reference plus, I think it was M, see, I believe it was M times Q double dot reference plus KP delta q ref. Let me just put it as q ref minus q plus kd q dot ref minus q plus n, right? And so when you wrote this down, plug that in here, what you notice is that n cancels off, and then you get a system which looks like this: q minus q ref plus kd q dot minus q dot ref plus kp q minus q ref, that is equal to 0, and then that becomes more like a spring mass damping system, kd. So then, it's the system basically behaves like a damper, and you can choose kp equals or kd equals 2 square root kp, and then it's going to be critically damped. So this is what we did for feedback linearization for an open loop chain. So open chain. Now we are talking about a closed chain. Okay, so either we have the minitar leg, the Atrius leg, or the digit bigger, or the digit leg. So I'm just going to write the actuated degrees: Q1, Q3, Q1, Q3, and then I'm going to just base it off Q1 and Q4, which is in my notes, but we can easily change it to Q3 and Q4 as needed. So minitar, Atrius. Okay, and the equation as I wrote down is mq double dot. Is it? So you can just quickly check this. It's just here. It's minus J transpose. Correct. Okay, so this is how the equation stands. We have basically our 4 plus 2, 6 by 1, 6 by 6, and 6 by 1. So we only can control 2 joints at a time, Q1 and Q3. And you can see that the complexity of this equation compared to that equation, right? So you could directly put U, and then you could control the system. Now this has become more complicated, even though there are only 2 degrees of freedom which I can control. It really has 6 equations. So how do you actually take this equation and control it using feedback linearization? So this is what I recommend. So first, what you do is figure out the control DOF. So for example, for the, let me call the control DOFs as theta. So for the minitar leg, it's going to be Q1 and Q3, right? For Atrius, it's going to be the same thing. So minitar, Atrius. For digit, it's going to be Q1 and Q4. Okay, so once you know that the control degrees of freedom, let's go to step 1, then rewrite the equations. Okay, you write them like this. So I'm going to write this as A theta double dot plus, so let me, sorry, my bad. So original equation is M minus J transpose J0 Q double dot F equals minus n g dot q dot. Okay, so you're going to rewrite them as follows: a11 theta double dot plus a12. I'm going to call this z. Okay, and I'll show you what z is. It's going to be a mixture of thetas and f. So I'll write it as z instead of theta double dot. And then a21 theta double dot plus a22 z equals p1 equals p2. So for minitar and digit, we'll have theta equals q1 and q3, and z equals q2, q4, fx, fy. For digit, sorry, minitar and atrius. For digit, we'll write theta as q1, q4, and then z as q2, q3, fx, fy. Okay, so we got this. And this is something which I would do in the derivation of equation stage. So it's very easy. You could do it later on also after derive, taking the values, but I just do it at the derivation stage so I can just pluck out the right a's. Once you do that, now what you can see actually is that you can do the following, which is from this equation, we can solve for z, right? So what we'll do is z equals p2 minus a21 theta double dot, and then I need to pre-multiply it with the inverse of a22. Okay, so that's z, and now we can take z and put it in this first equation sub. So we have a11 theta double dot plus a12. So z is a22 inverse a21 theta double dot plus p1. Okay, so now I can solve for theta double dot. It's going to be a11 plus a12 a22 inverse. So we have minus here corresponding to this a21 equals b1 minus a12 a22 inverse b2. Okay, so now what we have done effectively is we have written down this equation as we've eliminated z, and so it's only in terms of control variables theta 1, so q1 and q4 or q1 whatever. Now in these two equations, so this is, we can now see that if it's these two q1 and q4, we have torques at those joints. So now we can write this as, let me call this a tilde and this as b tilde and this theta double dot. So now we can write it as a tilde theta double dot equals b tilde plus u, where u is t1 and t, in this case it will be t1 and t4. For digit, it'll be t1 and t3 for minitar or atrius, right? So now we can recognize this form. Once you have this form, it's just a matter of writing the u as a tilde theta ref plus kp theta ref minus theta plus kd theta dot ref minus theta dot minus b tilde. So b tilde will cancel with that. So once you have this u, it will like essentially be the same as we have for control partitions. This form looks very similar to the control partitioning form. So once we have that, control proceeds as normal. I just use those. The key thing was to use those equations to eliminate these the extra variables which I don't care about, which is z, which are uncontrolled. I just get rid of them and then solve the equations and use that reduced equation now to do control. So I'll show you how the simulation looks for this. This is I'm going to show you how to control the leg. In this case, what I do here is, which is kind of not normal, which is in my main file, I actually derive the equations. Okay, so each time if I have atrius leg, I derive the equations and go for it. And then Minotaur, it does the same thing. And the reason why I need to derive the equations for separate cases is because, as I told you, that the first 2 degrees of freedom are the control degrees of freedom, right? So Q1 and Q3, case of Minotaur and atrius, are the control degrees of freedom. So I have to take them as Q dot to be the first variables in that to be Q1 and Q3. In case of digit leg, it's Q1 and Q4. So that's how I name them. And that ensures that when I derive the equations, my mass matrix, for example, would have the first 2 degrees, the first 2 equations corresponding to those first, the joints about which I can apply a torque. And the same for Jacobian. Okay, so then it generates the dynamics file, which is basically generating this mcg dot. The C and G is, the sum of that is capital N I wrote down. And then I have the RHS file, which basically uses the other one to get mcg and so on. So just split that. Usually I write one file here, I split it into 2 files. And the reason I split it into 2 files is because that just makes my life easy when I do the controller, which I'll just talk in a bit. So if I run this, now first derive the equations, then I choose the leg chosen, the atrius legs, which is from this. Okay, so in this case, it's supposed to do 2 things simultaneously. One is, I don't know if you saw it, maybe I should run it slower. Let me change the frames per second to 100. So it does 2 motions. So one, it's doing a swing motion from, I think, 30 degrees to minus 30 degrees to plus 30 degrees. But then it's also ensuring that the leg angle, the length of the leg changes from being 0.9 of its maximum extension to 0.75 mid stance, and then being 0.9 again. So hopefully it is slow enough that you'll see it. So it starts off. So derive the equations. Starts off extreme position, then increases the length, and then goes 0.5. And then if I change the leg to Minotaur leg, okay. And then you can also do it with the digit leg. Just that it's going to look very similar to atrius leg, just that the torques are applied at different places, so the angles will be different, which are going to track. Okay, so this is just saying what I wanted to be. It's basically 0.9 is the leg length at extreme positions, 0.6 mid stance. And the mid stance is defined such that my alpha, which is an angle made between the, I think it's the pin joint, and the average of the angles between the average of the angles between Q1 and Q3 is 0. It's basically in the file. I can show it to you. Should be in the file. Or link, not this. Reference. Okay, this basically solves for the reference motion. So what it does is basically it takes the desired length, desired alpha. Alpha is basically the angle made by the virtual leg length, which is the point joining the hip joint all the way to the tip of the joint. So if you draw a line there, that's the virtual leg length, and then the angle made by that length with the horizontal is alpha. And so I choose that L and alpha to be whatever I want. So it basically involves solving a kinematics problem such that I get that particular position and that leg length. And then once I do that, I basically use quintic polytraj. This is a utility within the robotics toolbox, which gives me a fifth order polynomial between 2 points. So use that. So that comes into here. And then once I have the reference motion, I can then do the integration with OD45. So within the 4-link chain RHS is my, let me open that. So within this 4-link chain RHS is my controller. Okay. And in this case, since it is the digit leg, I'm controlling T1 and T4. So if you look at the controller is where you'll find the equations I wrote down. So depending on the leg, I need to choose what Q dots are and what theta is being controlled. So for example, in case of Minotaur, it's Q1 and Q3. For digit, it's Q1 and Q4. Okay, so that's the reference is basically defined based on these. So interp, KP, KD, the same formula I wrote down is here, A tilde. And then torque is basically this A tilde, reference, KP, KD, B tilde. So it basically does control partitioning or feedback linearization. Okay, and then the torque puts out. So this is the torque. This is for the digit leg, I think T1. But it is, oh, where is that controller? Yeah, so it outputs, not this. Oh, sorry, my bad. Here it outputs T1 and T4 because you are applying torques at T1 and T4. Now I'm going to show you something different. So we'll run this with the Atreus leg, or let's do it Minotaur leg. Okay, and then remember that 4-link chain RHS had T1 and T4. So I'm going to run this now. So now it will derive the equations first. So it's deriving the equations. And then it rewrites the 4-link chain RHS file. So you'll see that it will not be T1 and T4, but it will be T1 and T3. Stop. Now let's go back to 4-link chain RHS. And so you see that it has updated this file. It's become T1 and T3. And that's why I need to rederive these equations every time I change the geometry of the legs. Because now the control is applied at T1 and T3 instead of T1 and T4. So so that's basically it on control partitioning for closed chains. Okay. Questions?